So including today, we have only 3 classes left. And in these 3 classes, what we're going to do is we're going to extend the concept of electromagnetic fields to other media. So we talked about electric and magnetic fields in free space, both static and time varying fields. And in the rest of the course, we are going to talk about electromagnetic waves in other media. And in the last class, what we did was we talked about one special type of uniform plane wave, and that was sinusoid. And the reason for doing that is if we understand sinusoidal electromagnetic waveform, we can analyze other waveforms easily, because using Fourier theory, we can express any other practical waveform in terms of superpositions of sinusoids of different frequencies. So that is why we'll focus on just sinusoids even when we move on to other media. And today, so you're going to get the final formula sheet, and as well as the new problem set. So 2 things. And in this formula sheet on page 4, okay, bottom right of page 4. So what you'll see is different parameters of a sinusoidal waveform that we discussed in the last class. Okay, so let's quickly review them. So when we say a sinusoidal waveform, it will be a waveform of this form. Electric field will be a cosine or sine. Similarly, magnetic field will also be a sine or cosine. And there has to be 2 independent variables. One is time, one is space. And to keep things simple, we are using only one spatial variable, x, y, or z. Plus, additionally, there could also be a constant in this phase of cosine. And so among the different terms we have here, the first one, this is called amplitude, and it's measured in volts per meter. If we're talking about a magnetic field, then the amplitude would be measured in amperes per meter. And omega is what we call radiant frequency, measured in radians per second. Beta is the phase constant, measured in radians per meter. Then we have time period t, which is related to the radiant frequency as shown here. And we have wavelength, which is denoted by lambda, and it is related to the phase constant beta. Temporal frequency, f, is denoted as f, and it is 1 over time period. And so we have 2 independent variables, t and z. One is time, one is space. And the form of cosine we have, it is pretty, the spatial and time variables are pretty similar, as you can see. So for the temporal case, we have a time period t. And for the spatial case, this is similar to the period in the temporal case. The lambda acts the same way t acts for the temporal case. The temporal frequency, we call it f, and the radiant frequency we call omega. Similarly, we have spatial frequency, reciprocal of wavelength, denoted by k, and it is 1 over lambda. So the similarity that you see are between time period and wavelength. So these 2 things are similar. One is temporal, one is spatial. Then we have temporal frequency and spatial frequency. These 2 things are also similar. Then omega and beta. These are the angular frequencies. Those 2 things are also similar. So one is for time, one case is for time, one case is for space, but the idea is the same. And there is, so at the bottom, you can see that there is one more term, wave velocity. It is the velocity at which the wave travels. We didn't discuss this in the last class, so today that's where we'll start. Okay, so let's start with wave velocity. So consider again a sinusoidal electric field. Let's say E equals E naught cosine omega t minus beta z ax. And so let's try to draw this, and we'll try to draw this for a specific values. For a specific value for omega, let's say it is pi by 2, and let's say beta is pi. If we draw this waveform, so let's first do it for t equals 0. And it's a function of z. It's a sinusoidal function of z. The wave looks like this, right? And let's say this point over here, this is z-axis, and this is z equals 0. This is a cosine. And so we are assuming that t equals 0. This graph is for t equals 0. And let's pick a specific point on this waveform. Okay, let's say we pick, it's kind of hard to see this. So this value is 0.5, and it happens at, if t equals 0, this happens at z equals 1 by 3. And now let's draw the graph for t equals 1. At t equals 1, what happens is the waveform will be shifted. So maybe it will be somewhat like that. And the point that we are interested in, that point will now have moved to the right. And let's say that point occurs at somewhere over here. This is 0.5. So as time increases, the point that we are keeping track of, it moves forward in the positive z direction. Right? So that part is clear. This is a forward traveling waveform. And so when do we get 0.5 for the electric field? So we're also assuming that E naught equals 1. So at t equals 0, when z equals 1/3, we get electric field value equal to 0.5, right? So we get that value of 0.5 anytime the total phase of the cosine equals pi by 3, right? So cosine pi by 3 equals 0.5. So what matters is the overall value of the phase of this cosine. So if we pick pi by 3 for this overall value, then that will be like tracking this point, particular point 0.5. If we pick some other value for omega t minus beta z, some other constant, then we might be tracking some other point, maybe over here, maybe over here. It could be anywhere. There are infinite number of constants that we could pick for this, and corresponding to that, there will be infinite number of points on the waveform that we can track. But any point that we pick, that will correspond to omega t minus beta z equals constant. And to see how fast or slow the specific point that we're tracking is moving along the z direction, what we can do is we can differentiate this with respect to time. So if we differentiate with respect to time, both sides, we get on the right-hand side, we get a 0 since we have a constant. And on the left-hand side, we get omega minus beta z. Sorry, we need dz by dt. Right, so that gives us which is what we denote this by V. This is the wave velocity. Okay, any question? So for a sinusoidal waveform like this, to see how fast the wave is moving, all we have to do is take the temporal radiant frequency and divide that by beta, the phase constant. We get the wave velocity, and it's measured in meters per second. Okay, so that is also in the formula sheet on page 4. You can see that. And so sinusoidal waveforms is what we discussed in the last class. And at the end of the class, we also talked about phasor transfer. And the reason for doing that is we've been discussing free space, and we analyzed everything in time domain. So for free space is a simple case. So analyzing everything in time domain is still simple. But now as we move on to other media for propagation, things can get a little more tedious if we analyze them in time domain. But in frequency domain, things become a little more easier. And so we want to move to frequency domain, but we don't want to use Fourier transform since we're dealing with just sinusoids. Phasor transform, it works the same way. So we will use just the phasor transform. And so what we did in free space was, this was a week ago, we talked about wave equation. This was for free space, and we did this in time domain. So we talked about free space width, where we had a source-free region. Source-free means that this conduction current density is 0, as well as the volume charge density is 0. And to get the wave equation, what we did was we started with a Maxwell equation, and we took the curl on both sides, right? And then we applied another Maxwell equation where we had curl of H. We also used a vector identity, right? And that led us to this wave equation, right? Second order partial differential equation is what we got. Now we are going to do the same thing, but we are going to do this in phasor domain because it becomes more complicated in time domain for other media. But the steps are exactly the same. Right. So when we talked about free space, we talked about only two parameters of the medium, that is free space. One was permittivity, epsilon naught, and the other is permeability, mu naught. Now, as we go on to other media, there will be three parameters. One is permeability, then the second is permittivity and conductivity. And today we are going to discuss what these parameters mean, because we've been using permeability and permittivity, but we've never actually defined them. Okay, so we'll start with what permeability actually means. So it tells us how easily a medium allows formation of magnetic fields. If it allows formation of magnetic fields within it easily, it will have high permeability. If it doesn't allow that easily, it will have low permeability. And to understand that, so I have this figure. So what we know is that any current carrying wire, it is a source of a magnetic field. And if we look inside an atom, there are electrons orbiting about the nucleus, as well as they are spinning in their axes. So any motion of electrons, since it's a charged particle, its motion can be considered as a current. So every electron moving in its orbit or around its axis can be modeled as a current carrying loop. So here what you see is many tiny loops like that. And each loop will have, it acts as a source of magnetic field. So you see that there is a magnetic field. The blue arrows indicate the direction of the magnetic field. But inside an atom, since there are many loops like that, they are all generating their own magnetic fields, but the magnetic fields are in random directions. So the total net magnetic field will be 0. Now, let's say what we do is we apply an external magnetic field with intensity H to this material. This is before an external field is applied. Now, after an external field is applied, because the field exerts force on the charged particles, so the loops will reorient. They will try to align with the direction of the external magnetic field, and their net magnetic field now might not be 0. So the external magnetic field will be enhanced. And some material will align pretty easily along the direction of the external magnetic field, but some material might not align that well with the external magnetic field. So the material where the alignment is strong like this, they have high permeability, and the material where the alignment is not that strong, that's a material with low permeability. So permeability determines how easily a magnetic field can exist inside a material. And so everything I said just now about this figure is written here. Now, the notation. So we saw that for free space, the notation for permeability is mu naught, right? We use subscript naught to indicate that it is for free space. For a general medium, we'll use the notation just mu. But its unit remains the same, Henries per meter. And so for other media, when we talk about its permeability, we can still talk about it in terms of the permeability of free space. So basically, we can write the permeability of any medium as permeability of free space, which is mu naught, times a scaling factor, mu r, which is called relative permeability. So mu r is a dimensionless quantity. Right? Any question? That's permeability. Now, the second term we have is permittivity. So just like permeability, what permittivity does is it talks about how easily an electric field can exist inside a material. So now consider the left figure here. So what it shows is a positively charged nucleus in an atom and an electron cloud around the nucleus. And in an equilibrium state, the electron cloud is more or less symmetrically distributed around the positively charged nucleus, so the net charge is 0. And what we know is that each charged particle acts as a source of an electric field. So each charge here, each electron and nucleus, they act as sources of electric fields, but the net electric field will be 0 because the negative charges are symmetrically distributed around the positive charge. And this is before an external field is applied. Now, let's say we apply an external electric field with field intensity E. Then we know that the electric field will exert force on these charged particles. So the negative charges move in one direction and the positive charge moves in the opposite direction. Now the charges are not, positive and negative charges are not symmetrically distributed anymore. So if we take their total contribution to electric field, that will be non-zero. So the external electric field will be enhanced by the electric field generated by these charged particles. And in some medium, the separation between the positive and the negative charges will be large. And if the separation is large, the electric field generated by that medium, these charges themselves will be high. In some medium, the charges do move in response to the external electric field, but they might not move that easily. So it's total separation of the charges, negative and the positive charges, might not be that large. So their contribution to electric field might be small. So this is a medium with high permittivity. This is a medium with low permittivity. So it characterizes or it quantifies how strongly a material produces an electric field in response to an external applied field. Right? Any question? No. Everything about this figure, so it's that I said is typed over here. Now the units and notation. So for free space, we've been using the notation epsilon naught. Naught subscript was for free space. And now for other medium, we'll just use the symbol epsilon. And epsilon can also be written in terms of permittivity of free space. So scaling factor epsilon r times epsilon naught. And the scaling factor is called relative permittivity of the medium, which is a dimensionless quantity. Yeah.
I'm just curious. So is the scaling factor ever greater than 1 or?
It can be greater than 1. Yeah. Okay, so the third quantity is conductivity. This is something that you already know from circuits classes, right? Conductivity, it quantifies how easily charges can move in a material in response to an electric field. And it is denoted by sigma, and it is measured in Siemens per square meter. And it is related to electric field intensity by this relationship. Conduction current density, J, equals conductivity times electric field intensity. So now, two things, permittivity versus conductivity. So permittivity is related to separation of positive and negative charges when we apply an electric field. And conductivity is also about movement of charges, but it talks about continuous motion of charges in response to external field. And that continuous motion of charges is what we call current. So conductivity is about current, whereas permittivity is about just separating positive and negative charges, but they are not in continuous motion. And when positive and negative charges are separated in response to an electric field, they store energy. It's like potential energy in a stressed spring. So they store energy, but when charged particles are moving, contributing to current, we lose energy. Energy is lost as heat dissipation. So due to conduction, there is always energy loss. So if we have an electric field, a sinusoidal electric field that starts out as like this. So in free space, we can expect, so this is, let's say for time, fixed time, t equals 0. We can expect it to go forever, like that. But if we have a conducting medium, if conductivity is non-zero, there is energy loss due to heat dissipation. And so the amplitude of this cosine will decline. It will decay. And so we'll talk more about that in a bit. Okay, so let's see what I have here. All right. Now what we're going to do is, for these other media that we just discussed, we are going to derive the wave equation, just like how we did it for free space. For free space, we did it in time domain. For other media, we are going to do this in phasor domain, but the steps are exactly the same. So first of all, we're going to start with the Maxwell's equations. They are also in your formula sheet now. Right? So the first step would be to take everything to phasor domain, right? So when we take this to phasor domain, what happens is E becomes, the notation changes first of all. We use subscript S in fields to indicate that we are in now phasor domain. And time derivative, remember, that becomes J omega. So the phasor transform of the first equation is, so curl of ES equals minus J omega mu HS. We converted our time derivative to J omega. And we're going to do the same thing to the second equation. So we have curl of H on the left-hand side. On the right-hand side, so that time derivative becomes J omega. And then we can factor out electric field. We can factor out ES. So we get that equation. And then the third one, third and fourth ones, they are pretty simple. When we were talking about free space, we set J equals 0 because sigma J is related to electric field and sigma. If conductivity sigma is 0, then J is 0. For free space, there is no conductivity. But now we are talking about media that have finite conductivity as well. Now, just like what we did for free space, we are taking the curl of both sides of the first equation, and then we use a vector identity. So we use the same vector identity last time also, and then a few things cancel. And where we have curl of HS, we are going to substitute the other Maxwell's equation here, which takes us to this final equation. This is the wave equation for the electric field, but it's in phasor domain or frequency domain. We can call it still wave equation, or since it's in frequency domain, there is another name for it, and that name is Helmholtz equation. That's another name. Now, so in this equation, what we are going to do is we are going to introduce a new constant, right? So we have on the left-hand side, partial second-order derivative with respect to space. And in the right-hand side, we have electric field, and then all this constant. That's just one constant. It's complex, but it's a constant, and we're going to call this gamma squared. That's pretty important, where gamma stands for propagation constant. And you can see that if we set sigma equals 0, how it reverts to the wave equation that we had for free space. Okay, so that constant is pretty important, gamma squared, and it is in your formula sheet as well. So if that is gamma square, right, this whole thing is gamma square, then gamma would be square root of this term. Okay, so let me go to the formula sheet. On the final page of the formula sheet, so you see permeability, permittivity, conductivity, and then the wave equation for the electric field and the magnetic field, and they are in phasor domain. And the constant that I just described, that is gamma square, where gamma is called propagation constant. And since it's a complex number, it has a real part and an imaginary part. The real part is, let me go back. Okay, so gamma equals alpha plus J beta. We denote the real part as alpha. Alpha is called attenuation constant. If conductivity in a medium, if sigma is non-zero, then alpha will be non-zero. Alpha is what attenuates the field. And then beta is the same thing that we had before. It is the phase constant. Imaginary part of the propagation constant is phase constant. The unit for alpha, the attenuation constant, is Nepers per meter, NP per m. And the phase constant, that's from before, so its unit is radians per meter. And we can also get the expression for alpha and beta. So how do we do that? See, we have two equations. So gamma square is all this, right? That is gamma square. So we expressed all this as gamma square, but we're also defining gamma as alpha plus j beta. So we can get another expression for gamma square. If we just take the square of this equation, right? We can do gamma square equals alpha plus j beta square. And then we can equate these two, right? We can equate those two expressions and we get a complex equation. We can equate the real parts, we can equate the imaginary parts, and we can solve for alpha and beta. Okay, that's a tedious process, but it's pretty straightforward. And the final values for alpha and beta are listed here, and it's on the final page of your formula sheet. Any questions so far? Okay, now just like what we did for free space, once we had the wave equation, we talked about the solution to the wave equation. We're going to do the same thing here. We have this wave equation in phasor domain. We'll talk about the solution to the wave equation. Okay, this is the wave equation for the electric field, and any expression of this form, some constant and then exponential minus gamma z, that will be a forward traveling electric field. Okay, and remember, gamma is a complex number, alpha plus j beta. And similarly, there will be a time domain expression as well. To get to the time domain expression, remember, we have to do the inverse phasor transform, which we did in the last class. And that's it. Now, there are many new terms and formulas. So what we're going to do is the rest of the class, we're going to apply these formulas in solving some problems. So we are going to look at some problems from problem set 9. The first problem, we already did this last week. Okay, so the first one, we're already done with that. So we're going to start with problem 3 today. All right. Now the formula sheet that you have it's in the final form on your in the final exam. This is what you'll be bringing. So you should get used to where different formulas are. And another thing is, since we'll be doing a lot of calculations in the phasor domain, things will be complex. So your calculator needs to be in complex mode. Now, this problem, as long as you have the formula sheet and the calculator in the complex mode, is pretty straightforward. So this is problem 3. What it's saying is that a sinusoidal uniform plane wave of frequency 1 megahertz. So what is given is there's a frequency 1 megahertz, that means 10 to the 6, right? And the sinusoidal waveform propagates in the AX direction. The electric field intensity is oriented in the AY direction. So what does this mean, first of all? The electric field intensity is oriented in the AY direction. So what we know is that electric field will be in the AY direction, and it propagates in the AX direction. So remember, we used to do this, right? Cosine omega t minus beta x. And we would have an amplitude also, E naught. That's what we used to do in free space. But now we are in a different, it's a general medium. So there will be an additional term because of the attenuation factor. And to understand that, so let's look at this general solution for the wave equation. We said that the solution to the wave equation is ES equals E naught e to the minus gamma z. Okay, this is not exactly related to this problem, okay? So e to the minus gamma z ax, right? This is in the phasor form. This is the solution to the wave equation. And from the phasor form, we have to get the time domain expression. What would be the time domain expression? So first, let's expand this gamma, because gamma equals alpha plus j beta. So we have minus alpha z minus j beta z ax, right? And then, so how do we go from the phasor domain to time domain? So what we need to do is we need to multiply by e to the j omega t, and then we need to take the real part of that. So electric field in time domain will be real part of e to the j omega t e to the minus alpha z minus j beta z, and then ax. First, let's combine all the exponentials. The complex ones, let's keep them together, and the real ones, let's keep them separate. So two of them has j's in the exponent, one does not, right? The one that does not have j, that's a real term. So let's keep that separate. And the other terms are e to the j omega t minus beta z. Okay. Now we are taking the real part of all that. So when we take the real part of something, any real term that is being multiplied, that we can just copy, right? So this part, e to the minus alpha z is real, so we can just take it out. Ax is also not complex, so we can also move that out. So we need to take a real of e to the j omega t minus beta z. This is the only complex term there, right? And to take the real part of a complex term, what we do is we take the cosine, remove that j, and copy the rest. That is all right, but I dropped E naught. See, we have this E naught, right? So that needs to be copied over. Okay, that is a real term. We should keep that. So let's reorder the terms here. So we have this amplitude E naught, and then we have e to the minus alpha z, and then we have cosine omega t minus beta z ax. We are already familiar with this part. This part is just a cosine wave that is traveling in a certain medium. It's traveling in the positive z direction, right? And then we have an additional term here, e to the minus alpha z. So what does that term do? If we plot just this part as a function of z, this is an exponential decay, like that, right? And then if we plot this cosine, this is a sinusoidal waveform with a constant amplitude. If we multiply them together, so we get a sinusoidal waveform that is attenuating. Right, all this to show that All this to show that the form, the time domain expression for the electric field intensity is, it is E naught e to the minus alpha z cosine omega t minus beta z. And if it's oriented in the x direction, it will be like that. Now, let's go back to problem 3 that we were working on. In the problem 3, what it says is that the field is oriented in a y direction and propagating in x direction. So for problem 3, our electric field in time domain will be e to the minus alpha, not z, but x. It's traveling in x direction. And then it's oriented in y direction, so it will be y. So we know the form for the electric field from the problem statement. So this will be the form, but what we don't know are alpha, beta, omega, E naught, right? So what is given is frequency is given 10 to the 6. What else is given? At t equals 0 and x equals 0, the electric field intensity is 10 volts per meter. So by specifying that, it is giving us the value for E naught. Yeah.
For some reason, I can't find the equation that you use in the board.
Which one?
The equation ES equal E naught times E minus gamma Z AX. Is that, I don't see that in the equation sheet. Yeah, that on the top one.
If look in this, it should be in the solution to the. Yeah, it's not given. So you can add it over here. But it's not always going to be Z and X like that, right? So depends on which direction it is traveling. Okay, so T equals 0, X equals 0, field is 10 volts. This is in time domain, what we just wrote. In the phasor form, the field is ES, E naught, e to the minus gamma Z. Okay, so at Z equals 0, we have 10. So that tells us that E naught equals 10 volts per meter. So we found one parameter. We also know omega because frequency is given in hertz. So frequency equals 2 pi f, that equals 2 pi times f is given as 10 to the 6. So that is frequency. Now let's find the important ones, alpha, beta, and gamma. And in the formula sheet, there are expressions for
E to the S.
what's your question?
Go back.
Okay. I'll go back in a bit. So for alpha and beta, so there are two ways you can do it. The formula is right there, right? The formula for alpha is there in terms of omega, mu, epsilon, sigma, and we know all those parameters. So we could just plug this in your calculator and you could get the value for alpha and beta. And there is another indirect way, but it actually turns out to be simpler. That would be finding gamma squared first, because since omega, mu, sigma, everything is known, we can plug this expression in our calculator and we can get gamma square, right? And if we have gamma square, we can also take the square root of that to get to gamma. And the real part will be equal to alpha. imaginary part will be equal to beta. So we have two ways we can do this. What was your question?
Sorry, the second line there, the units are, the variables that's in the, is negative, what is it, z or the?
Over here, that's gamma z. Yeah.
And is gamma a real value or?
Gamma is complex. Gamma is complex. So you should get used to this. Gamma equals alpha plus j beta. All right. Now, so since everything is given, we can actually plug in all the numbers here, right? Omega equals 2 pi 10 to the 6. Then we have another omega that will also be 2 pi 10 to the 6. And we have sigma given. Sigma is 3.3379 times 10 to the minus 4. What else? So epsilon. So what the problem says is it gives us epsilon r instead of epsilon, right? Epsilon r is the relative permittivity. So epsilon will be that epsilon r times epsilon, so not. So it will be epsilon r is given as 8 and then 8.854 times 10 to the minus 12, the free space value. Similarly, we have mu. Again, mu is written as mu r times mu naught, and mu r is given 80.89, and then mu naught is the free space value, so it is 4 pi times 10 to the minus 7. Can you type it in your calculator? And the difference between alpha and beta, if you type 1, for beta, all you have to do is change the sign to plus. That gives you beta. I actually wrote down the numbers. So this should be equal to 0.1885. And the unit for alpha is Nepers per meter. And similarly, we can find beta by using plus instead of minus there, and that will be 0.5655. And that is radians per meter. That is one way of getting alpha and beta. And the other way is, now let's go back to the formula sheet. So if you don't want to enter those big, that big expression on your calculator, so you could try this, right? So because we need gamma, not gamma square, you will have to do square root of this, right? And if you do this, if you enter all this in complex mode on your calculator, you should directly get 0.1885 plus j 0.5655. You need to get this in the rectangular form like this. Right, any question? So we found alpha, beta, gamma. After that, velocity is pretty simple. It's omega by beta. and that will be 1.111 10 to the 7 meters per second. Electric field. Okay, so we found that E naught, the amplitude is 10, and then we have e to the minus alpha 0.1885 x, and then we'll have cosine omega is 2 pi 10 to the 6 omega t minus beta 0.5655 x, and the field is in the y direction, and this is volts per meter. Now, all of this came from the direct formula, right? Now, the next one is magnetic field intensity. That is, we have to take a few steps to find the magnetic field intensity. And so this will be similar to what we did in free space. Remember, if we had electric field intensity, we took its curl to get to the negative derivative of magnetic flux density, and then we integrated that to get to the magnetic flux density, right? Because our equation, Maxwell equation that we were using for free space was this: curl of E equals minus mu naught, right? So we had that. So that's why we took the curl and we had to take the, we had to integrate. Here we are in phasor domain. So in phasor domain, our equation is curl of ES equals minus J omega mu naught HS. So we could still do this, use Maxwell's equation in time domain and take the same steps that we did before, but that will be a little more tedious. It's a lot more easier to do this in phasor domain because all we have to do is take the curl of electric field intensity in phasor domain, and then we don't even have to integrate because, integration is getting replaced by, the derivative is getting replaced by multiplication by J omega. So we'll do this in phasor domain, right? So since we have electric field in phasor form, electric field equals 10 e to the minus gamma z, and not z, it is x. Okay, more space here. So do this in phasor domain. So I wrote gamma instead of writing all that long complex number. It's easier to do that, right? Now we take the curl of this. And the field is in the middle row only. Okay, so when we take the curl, so what do we get here? We only get the z component, right? Traveling in x direction and the field is oriented in y, so we're going to have only z component. So to get the z component, we take derivative this way first and then this way. The second way will be 0. We just need this part. So all we need is derivative with respect to x, 10 e to the minus gamma x, and it will be in z direction. So the derivative will be minus 10 gamma e to the minus gamma x az. Right? And now from Maxwell's equation, we know that this has to be equal to negative j omega mu naught hs. So that means to get hs, what we have to do is take 10 gamma e to the minus gamma x az, and then instead of integrating, we're just dividing by j omega and also mu naught. Yeah.
So, and at the very beginning, you put a phase and train form. The equation of per ES is minus J omega and mu, not mu naught. So,
That's right. Thank you. So I'm used to free space. So it's not mu naught anymore. It's everywhere. We should remove that subscript because now it's a general medium. And here also. Everywhere. Okay, so now we have all the parameters already. We know gamma. Gamma is complex, remember. And so again, another complex number over here. But we can do this in one line on the calculator, right? In complex mode. And you should get, I wrote it down. Right, so let's write just this part first, because the other part, e to the minus gamma x az, that electric field intensity also has that component, right? The difference, and e to the minus gamma x, electric field also has that. The difference is this amplitude. For electric field, the amplitude was real. Here, the amplitude is now going to be a complex number. So if you plug this part, just this part on your calculator, what you should get is, you should write that in the polar form. And I'll explain why. Some numbers we need in rectangular form. For example, gamma, we need in rectangular form because its real part gives us alpha, imaginary part gives us beta. For the amplitude of HS, we will do polar form, 9.3, and the phase will be minus 0.3218. That's just a complex number. So everybody understands that this is the same as right? So that's just another way of writing. Okay, so that's the complex number we're getting. And then the other part is e to the minus gamma x az. Now, why we did that in polar form is because this is in phasor domain. We need to go back to the time domain. To go back to the time domain, what we do is we keep only the real part as the amplitude. Anything that is any phase, it gets absorbed by the phase of the cosine that we'll eventually get, right? So it has to be in phasor form. Also, let's expand that gamma as well. So gamma was 0.1885x minus j 0.5655x az. Okay. So we'll write all the real part together and the complex part together. So the real parts are, one is this and then this part, right? So let's write them in the front. And then combine the complex exponentials. So we have minus j 0.5655x plus 0.3218. It's a lot of steps, but if you look at every single step, it's pretty straightforward. So any question about that? We put the real parts together and the complex exponentials on one side, right? So that we can move to the time domain easily. Because what do we do to move to the time domain? Now we need to multiply this by e to the j omega t, right? And then take the real part of that. So the time domain expression for H is going to be real part of. So we take all this multiply by e to the j omega t. So since we multiplied by e to the j omega t, another complex exponential here, so we should combine this with the other complex exponential we have. So put them together again. So j omega t, in fact, also for omega, let's write the actual value because we know it is 2 pi 10 to the 6 and then t. And then we have minus 0.5655x minus 0.3218. Okay, that's just multiplication by complex exponential. As we take the real part, now what happens? This part, the front part, which is not complex, we just copy that part. As it is. And then for the complex exponential part, complex exponential becomes cosine. And we get rid of that j. And the direction was AZ. Okay, now let's compare this with the time domain expression for the electric field. So how are they different and how are they similar? The attenuation factor is this decaying exponential, right? They are exactly the same. They attenuate at the same rate. Their amplitude is different for H and electric field. And then the cosine part, most of the things are similar. This omega t part is the same. This x dependent factor is the same. However, magnetic field has this additional phase, right? Electric field does not have that. So electric field and magnetic field are now, they are out of phase. They are not in sync. This is still linear polarization. We probably won't talk about that. Any question?
This works because they're playing, right?
Works meaning?
I find people use phasor.
Phasor form? Only for sinusoids, yes. If it's not the sinusoids, we can do Fourier transform and then the same analysis carries over.
There's like it's hard to add, right?
There might be. So we have 10 minutes left. Now the final part in this problem, so what we already noticed is that electric field and magnetic field, they are out of phase. And so there is a term called intrinsic impedance. Just like in circuits, we have the ratio of voltage to current. Here, we have intrinsic impedance, and that is the ratio of electric field to magnetic field. And so they are in phasor. So two things you have to be very careful. They are in, first of all, in phasor domain. It is defined in phasor domain. And second, I did not use arrows because I'm not using them in vector form. So what we do is we just take the magnitude. We drop the direction for this formula. Okay, this is intrinsic impedance, and we denote this by the symbol eta, and its unit is, it is ohms, it's impedance. Okay, now what is the impedance for this problem? So we have to go back to the phasor form for ES, and it is right here. This was electric field, so let's copy that. And then we copy the magnetic field in phasor form. We cannot do this in time domain. First copy those, and then remember, we don't take direction. This formula does not have directions, so we should drop the directions from both, and that gives us impedance. And we should always have the e to the minus gamma x part will always cancel because they both have that. So this part cancels. I already separated for the electric field. All right, so let me expand this. So what we have here is e to the minus 0.1885x minus j 0.5655x. So the parts that will cancel are, so this entire part, right? This part cancels and this cancels, but this part does not. The magnetic field has additional phase that will stay there. So we are going to get a complex number here. It is 10 divided by okay, and that is going to be equal to 1071.5, and phase is 0.3281. And the phase of the impedance, this is the phase difference between the electric field and the magnetic field. Just like in circuits, the phase of impedance tells you the phase difference between voltage and current. It's like that, electric field and magnetic field. Right. Any question? Since we have only 5 minutes left, you can work on a very short problem. Okay, for classwork, so look at problem 2 and just find gamma.